Swayam Prabha. Digital India. Educated India.
Hello everyone, once again I welcome you all to MSB lecture series on advanced transition chemistry. In my previous lecture, after completing valence bond theory, I gave introduction to crystal field theory by going back to historical background and looking into the contribution of several physicists along with chemists to define this very important theory to explain almost all aspects of coordination compounds. So, now let me continue from where I had stopped. I shall introduce soon Jahn-Teller theorem also in this lecture. When we consider 6 coordinate octahedral complexes, this is how crystal field theory investigation began by considering 6 coordinated complexes. If we consider any transition metal complex for that matter, the 5d orbitals of these cations are degenerate and have equal energy. The electric field around a metal cation results in the total energy level being lower than that of a free cation because of the electrostatic interactions, and there will be some repulsive interactions because ligands are carrying electrons and also metals have electrons. As a result, what happens, the negative electric field destabilizes the system and compensates for the stabilization to some extent. Now, it would be interesting and informative to consider 3 geometries: octahedral field, square planar as well as tetrahedral field. And for convenient and better understanding, let us try to confine octahedral molecule, a square planar molecule and a tetrahedral molecule inside a cube with center occupied by metal ion and surrounding 6 ligands in case of octahedral and 4 ligands in case of both square planar and tetrahedral geometries. And these green spheres represent ligands and their approach towards the central metal atom to establish metal to ligand bond, and same thing here and same thing here. If you just look into octahedral molecule, before we begin we should also consider these Cartesian coordinates, and at origin we have kept the metal center. Now we can see how the ligand approach direction are coinciding with these Cartesian coordinates. Why this is important? When we place all 5d orbitals at Cartesian coordinate, we know that dz square is along z axis and dx square minus y square is along x and y axis, and dxz, dyz and dxy are between the respective axes. This is how the orientation. And now if you just look into the direction of approach of ligands here, and it is very easy to understand how these ligands will be interacting with 5d orbitals. That means in case of octahedral, these 6 ligands will be interacting with 2 orbitals that are coming in their way, that is dz square and dx square minus y square, whereas other 3 remaining orbitals such as dxy, dyz and dzx are in between the axis. As a result, what happens? They are having much lesser interactions, and this is where the splitting of d orbitals into Eg and T2g, with T2g having slightly lower energy and then Eg having higher energy comes into the picture. Now let us consider a square planar complex. In this one 4 ligands are approaching, and if we assume this molecule is placed with principal axis being Z So, in this case what happens when the 4 ligands are approaching the metal ion, they are approaching from x, minus x, y and minus y direction. So, in this case what happens, since no ligands are coming along z direction, that is least affected, that means, and then rest is very similar to what we saw in case of octahedral complexes. Now, let us consider tetrahedral complex in which 4 ligands are occupying alternate corners of cube, and when these 4 ligands are occupying alternate corners of cube and not this one, you should ignore this one. So, one here and one here and one here. So, these 4 ligands are approaching the metal from alternate corners, and when they approach and establish bond, we will end up with a regular tetrahedron with regular tetrahedral angle here. So, in this case again if you place all the 5 orbitals along this Cartesian coordinates depending upon their orientations, and you will notice clearly that dz square and dx square and y square are not overlapping directly with any of these 4 ligands. In contrast, dxz and dyz and dxy would be having little larger overlapping with the direction of approach of ligand. As a result, here the energy levels reversal takes place compared to octahedral. This is what Kramer also depicted much before fully prepared crystal field theory was proposed by Van Vleck. So, in fact, this observation was also made by Kramer and others when they were working on crystal field theory before Van Vleck added all these ingredients to explain crystal field splitting in all geometries. So, this is octahedral, this is square planar and this is tetrahedral. Now, you can see in this one, this is for octahedral and this is for tetrahedral, and if you see the magnitude also in case of octahedral and CFS in case of tetrahedral, a remarkable difference is there, and in fact you can see the difference is quite considerable. That means usually weak field ligands form tetrahedral complexes, whereas strong field ligands prefer octahedral complexes. And whenever we come across a tetrahedral complex, usually the ligand field is smaller and the splitting is smaller, and there may be 1 or 2 exceptions, but nevertheless this is followed all through uniformly. So, now let us look into the magnitude of crystal field splitting, and of course since it can explain the transitions, because crystal field theory says that electrons are no longer degenerate in d orbitals and it is split into 2 or more levels. As a result, what happens, one can anticipate electronic transition. Since one can explain electronic transition, we can as well explain color of the complex using crystal field theory, and color of the complex depends on magnitude of this crystal field aberration energy. When we consider a metal, larger metal, and we expect larger CFSE, and metals with higher action state will be having larger CFSE, and for understanding the color of the complex and magnitude of CFSE, we should look into the positions of ligands in spectrochemical series, and this is a spectrochemical series for few ligands. I will be giving a consolidated spectrochemical series much later, and if you see here, among them chloride is the weakest ligand, and then fluoride comes, then water comes, and then ammonia, ethylene diamine and nitrate N bonded one, and the cyanide. So, here crystal field stability is also increasing here, and the ligand field strength is also increasing here. Now, what it says is weak field ligands, low electrostatic interaction, as a result crystal field splitting will be very small, and high field ligands, high electrostatic interaction between the ligands and the metal ion, that results in large crystal field splitting. You can see here how steadily it is increasing as the ligand field strength is increasing. So, that means it can also give you the magnitude, and also it can give you idea about the nature of the ligands, whether they are weak ligands, whether they are strong ligands, whether they are of intermediate in nature. So, this is the origin of spectrochemical series, and here you can see here hexafluorochromium 3 minus is there, all are octahedral complexes, only ligands have been changed here. When the ligands have been changed from fluoride to water, water to ammonia, ammonia to cyanide, and color also changing from green to violet to yellow to again yellow, and you can see the separation is steadily increasing. That means this clearly shows cyano complexes are much more stable compared to fluoro or halo complexes in general. So, now let us look into the electronic configuration in octahedral field. When we try to ionize and generate cationic metal ions, what would happen is first s electrons are lost, and then that means 2 electrons present in n plus 1 s orbital will be lost, and if further oxidation takes place, then the electrons will be in a sequence removed from inner d orbitals. For example, titanium 3 plus, we have 3d2 4s2 electronic configuration, we are left with 1 electron, so it is a d1 system. Similarly, vanadium 3 plus, if you consider, it is a 3d2 4s2 electronic system. If you remove 3 electrons, it is a 3d3 4s2 electron system, and if you remove 3 electrons here, we will be left with the d2 system here. And then in case of chromium, we have 3d4 4s2 system, and if you remove 3 electrons, we will be left with d3 system. And first 3 electrons are in separate d orbits with their spin parallel. That means while filling electrons, Hund's rule is followed, and 4th electron has a choice. For example, if you have 3 electrons, automatically they will go to individual orbitals, separate orbitals, and the 4th electron comes, it has a choice of going to 4th orbital, or it can also get paired, something like this. So, that means here we have to introduce one more term, the pairing energy. Higher orbital if delta is small, that means high spin complexes, and lower orbital if delta is larger, low spin complexes will be there. That means in case of weak field ligands, this separation is small, as a result what happens, electrons would be promoted easily rather than getting paired. That means the CFSE is much smaller than pairing energy. Okay. As a result what happens, it is instead of getting paired, so it will go and occupy higher position. And then in case of strong field ligands, we have larger separation is there. As a result what happens, pairing energy will be much smaller than the promotional energy. As a result what happens, they will be get paired instead of going to the higher orbital. So, that results in low spin complexes. In contrast, in these cases where ligand field is small and this separation is small, it is easy to promote electron, we ended up with high spin complexes. And you can see that again magnitude can be very nicely compared here, one with hexafluorocobaltate here and your hexacyanocobaltate here. So, you can see one is the weakest ligand, one is the strongest ligand, and that is reflected in the magnitude of this CFSE. And this compares 3 important geometries we come across among coordination complexes. This is a typical octahedral complex, and here the corresponding orbitals have shown with relative orientations, and here we have EG set, we have T2G set, and in case of tetrahedral exactly opposite takes place, and E are lower in energy and T2 are higher in energy, but the magnitude is smaller. And then in case of a square planar, what happens, further splitting takes place, and mostly D8, majority of them are low spin complexes with an exception of a few nickel 2 plus complexes. For example, if you take palladium 2 plus, platinum 2 plus, iridium plus and gold 3 plus and also rhodium plus, most of them they possess this square planar geometry. So, now let us move on to John Teller theorem. Herman Arthur John and Edward Teller, full name, okay. Mostly books introduce them as John Teller, but actually the full names are Herman Arthur John and Edward Teller, published about distortions in the geometry of octahedral molecules in 1937. It states that, I quote, any nonlinear molecular system in a degenerate electronic state will be unstable and will undergo distortion to form a system of lower symmetry and lower energy, thereby removing the degeneracy. So, that means this is called as John Teller distortion, and especially when we have uneven occupation of electrons in EG orbitals or E orbital, this is what exactly happens. That means odd electrons, if they are present in D4 system or D9 system, this John Teller distortion is more pronounced. Ideal examples are D4 system chromium 2 plus and D9 system with copper 2 plus. Is it T2G orbitals or EG orbitals or both? That means here the question is, how the Jahn-Teller distortion is affected. Is it because of filling of T2G orbitals or filling of EG orbitals or both? Let us try to answer these questions. In an octahedral ligand field, the T2G orbitals are at lower energy than EG orbitals. This is due to the orientation of T2G orbitals away from the ligand direction that you are all familiar already, whereas the EG point along bond axis, okay, EG Z minus Z, X minus X, Y minus Y. The shielding effect this has on the electrons is used to explain why the Jahn-Teller effect is only important for the EG level with odd number of electrons. The Jahn-Teller distortion is well documented in the case of copper 2 complexes as they are D9 system with 3 electrons in EG level. So, that means when we have 3 electrons in EG level, we have 2 options of filling them. That means I can put 2 electrons in dz square, or I can put 2 electrons in dx minus y square and 1 electron in dx minus y square and 1 electron in dz square in this case. So, what would happen? Let us say I put 2 electrons in dz square and 1 electron in dx square minus y square, so that it has D9 electronic configuration. In this case, what is the sequence of this kind of arrangement on stability of the complex? Now, when 6 ligands are approaching the metal ion, what happens, because I have put 2 electrons here, those approaching from Z and minus Z direction would experience maximum repulsion and try to stay a little away from the metal center, whereas here, since only 1 electron is there, 4 ligands approaching along X minus X, Y minus Y would undergo or experience less repulsive forces. As a result, they come little more closer to metal ion compared to what we will see along Z direction. On contrast, here other way around happens. So, here if you put 2 electrons in dx square minus y square orbital and 1 electron in dz square, here 4 electrons approaching the metal from x minus x, y minus y direction experience larger repulsive forces, and as a result what would happen? They will stay away from the metal ion relatively compared to 2 ligands that are approaching along z direction. They will come little closer as they have to experience repulsive forces because of only 1 electron present in dz square. So, that means here we have 2 longer bonds and 4 shorter bonds, and here we have 4 longer bonds and 2 shorter bonds. You can decide yourself which would give more stability, having 4 weaker bonds and 2 stronger bonds, or 4 stronger bonds and 2 weaker bonds. That means tetragonal elongation is more pronounced when metal ion has an option compared to tetragonal compression, because here it will be little bit less stabilized because you have 4 longer bonds and 2 shorter bonds. So, with this information we call this as Z. Okay, you can see something like this. We can see this one Z elongation, 2 long bonds and 4 short bonds will be there, whereas in this case Z compression happens. Okay, that compression means basically it comes like this. Case of Z compression, elongation means it goes like that. When you are pulling up in Z direction, those ligands will come closer in the plane. On the other hand, if you compress, this Z direction along the axis will be coming closer and they will be expanding. So, Z compression happens in this case. Let us look into some examples where we observe these Jahn-Teller distortions. I have listed some examples here, CuF2, CuCl2, CuBr2, and here in all of them the metal ion copper is in +2 state, and you should not assume just by looking into the composition that they are linear molecules. No, in 3 dimensional all of them are surrounded by 6 fluorine atoms or 6 halogen atoms in general in all these cases. So, that means here if you look into the crystal structure of CuF2, that means copper is surrounded by 6 fluoride ions, you should remember. 4 fluorine atoms at a distance of 193 picometer, whereas 2 fluorine atoms are at a distance of 227 picometer. So, that means here they are 2 are longer and 4 are shorter, you can say it is tetragonal elongation. But if you look into CuCl2, again 4 bonds are at 230 picometer and 2 bonds are at 295 picometer. These 2 are longer and 4 are shorter, again tetragonal elongation. In case of bromide, you can see 4 shorter bonds and 2 longer bonds along z direction. So, in all these cases we invariably see tetragonal elongation, and same thing is true in this case as well. And that can be extended to D4 system also. D4 system, Jahn-Teller distortion is slightly less pronounced because we have only 1 electron here, whereas here we have 3 electrons. So, nevertheless it also shows Jahn-Teller distortion that is reflected in this bond parameter. If you just look into it, 4 bonds at 200 picometer and 2 bonds at 243 picometer. Similarly, if you look into this molecule here, 4 bonds are 214 picometer and 2 fluorines are at 200 picometer. So, that explains, that means is it possible to see tetragonal compression as well? Yes, there are examples where we come across tetragonal compression as well, but if tetragonal compression is there, it is very difficult to predict. Probably it is because of solid state effect. What is solid state effect? By assuming tetragonal compression, probably the packing will be very efficient and they can be densely packed, and as a result what happens, lattice energy increases and stability increases. In those cases wherever the energy gained through lattice energy by having compression, if it compensates the energy loss due to Jahn-Teller elongation, in those cases what would happen? One can observe tetragonal compression. There are examples for tetragonal compression as well, but there you may not be able to explain unless you look into the solid state effects, or one can verify that one through spectroscopic measurements. Electronic spectrum one should record and look into transitions, and sometime it can guide you. Complexes of the type I have shown here, complexes of the type M2, Pb, copper, NO26 shows temperature dependent Jahn-Teller distortion. For M equals cesium shows Z elongation below 285 Kelvin with complex ion adopting tetragonal symmetry, whereas for M equals K, potassium distortions occur at below 273 Kelvin. So, that means here temperature assisted Jahn-Teller distortion one can see, and similar distortions were also observed with M equals rubidium at less than 276 Kelvin, and in the case of M equals thallium at less than 245 Kelvin. And then that means above these temperatures the molecules appear octahedral due to the dynamic Jahn-Teller effect. So, that means low temperature what happens, the splitting happens, distortion happens, tetragonal distortion happens, but higher temperature it does not happen. So, this is called dynamic Jahn-Teller effect. Let me stop here, continue discussion on Jahn-Teller distortion in my next lecture. Until then, have an excellent time reading about crystal field theory.